We're continuing with section 13.6, a survey of the quadric surfaces, this time elliptic paraboloid. So if you look at this equation, z equal to x squared, x over a to power 2, and plus y over b to power 2, if you intersect, find the cross sections for z equal to a constant. Oh, can c be bigger than less than 0? C cannot be less than 0. So let's say for c bigger than 0, find all the cross sections. The cross sections will look like this. So these type of cross sections are going to be parabolas and ellipses. Please note, if you want to find the cross section with z equal to 0, then this is the and this would be the equation, and then solving for, let's say, y, you get subtracting solving for x and y, you get x equal to y equal to 0 also. So the cross section at z equal to 0 is going to be the point 0 and 0 and 0. Why didn't I solve for y? Because if I had solved for y, I would have had x over a to power 2 equal to a negative number, and that's not possible. Or the other way around, if I solve for one of them, I would get and squared equal to negative of the other squared. So the only way this equation holds is when all the x, y, z's are 0. So how about if I set x equal to a constant? X equal to a constant c. Then the equation becomes z equal to a c over a to power 2 plus y over b to power 2. This is a parabola with, the variables are z and y instead of x and y that you're familiar with, but still a parabola. This part is a constant, and this is the y squared over b squared and equal to z. So a term plus y squared over b squared is going to be equal to z. So these are parabolas, and it's sort of symmetrically. If you set y equal to a constant to find the cross sections with planes y equal to constant, then you end up with parabolas also. So what we learned is that in two ways there are parabolas, cross sections are parabolas, and one way there are ellipses. Something interesting to discuss, and since you solved for z in here, z can be considered as a function of x and y, and it will basically functions for higher variables. And if you can functions of two variables to one variable, you still can graph it as a surface, and the graph should satisfy the vertical line test, and so this one will satisfy the vertical line test. Other things is that when a is equal to b, the horizontal intersections are circle. And this is the picture. If you see all the cross sections, if you take any plane that is parallel to YZ or XZ, you get parabolas. If you take any horizontal plane that is parallel to XY, you get ellipses. And then as when you intersect with XY plane, you only get 0. Oh, one thing that I didn't say is that if you intersect with any horizontal plane that is below the XY plane, you get nothing, basically, as we discussed it before. Now let's discuss hyperbolic paraboloid. And so how does this one work? Let's say z equal to a constant, z equal to c, and then you get x over a. So these are the y over b to the power 2 equal to c. This is a hyperbola. And so for z equal to c, you get a hyperbola. Interestingly enough, if first of all, if z is not equal to 0, and so if c is bigger than 0, the opening of hyperbola goes one way. If c is less than 0, the opening of the hyperbola goes the other way. But what happens when c is equal to 0? So let's try that too. Z equal to 0. So this is the xy plane, and you get this. So unlike in the previous the elliptical paraboloid, this one you can actually solve when z equal to 0. So you get x over a is equal to plus minus square root of plus minus y over b, because when you take the y over b to the power 2 to the other side, it becomes positive, and you take the square root and a plus minus appears. This is two lines, basically, one with the plus, one with the negative, that they intersect at 0, 0, 0. So what if I find the cross sections with x equal to a constant? Then we get z is equal to c over a to the power 2 minus y over b to the power 2. See, again, here c over a to the power 2 is just a constant, and therefore we get a parabola again. And same way works when y is equal to when we intersect with y equal to constant planes and find those cross sections. And so let's write it out in a clean way. So if x is equal to c, you get a parabola, but it's going to be looking downward. If you set, because if x is equal to c, you have negative y squared over b squared. And then if y is equal to c, you get parabolas, but they're looking upward. If you set z equal to c, they're hyperbolas, except that one at the, and you see the middle plane down there. That's going to be the two lines, basically two intersecting lines. And so if you put these together, you get you realize that it looks something like that. It's one of the most difficult ones to basically illustrate by hand, and it always looks better when a machine does it. But it's also called saddle surface. It also passes the vertical line test. See, I can solve for z in here. Therefore, z is a function of x and y. Others, I heard people call it Pringles. That works too, but saddle is the best description of that, and it's the name of it basically. It just looks like a saddle surface. It's not, and origin is not the is not a maximum point. It's not up of top of the hill or bottom of an alley. It's just in one way you go downward to origin, and one way you go upward to reach the origin. So basically it should kind of remind you of an inflection point from calculus of single variable. So let's discuss hyperboloid of one sheet. So hyperboloid of one sheet, let's put in x, and that's the equation x over a to power 2 plus y over b to power 2 equal to z over c to power 2 plus 1. And so if I set x equal to c, the equation becomes c over, let's change k again. K over a to power 2, because I have a c over here, constant c, plus y over b to power 2 is equal to z over c to power 2 plus 1. And so what is this equation? If I take, if I put again y squared over b squared minus z squared over c squared and equal to 1 minus k over a to power 2. This looks like a hyperbola. Now, same routine works if I set y equal to k. Very similarly, you arrive at a hyperbola. What happens if I set z equal to a constant, z equal to c? So if I set z equal to constant, not c but k, and then you end up with x squared over a squared plus y squared over b squared equal to k over c to power 2 plus 1. And so this is an equation, and this is always bigger than 0. So basically, the right side is always bigger than 0. Therefore, you always get ellipses for that, for this one. So we're saying cross sections are hyperbolas, and in one way it's the ellipses. The ellipses are changing. It's not like what we saw with cylinders, and so the ellipses are smaller down in the middle, and they go in a, basically sometimes I put in the easiest one that I can think of, and I see the ellipses. If I put different k for z, they're increasing, but then cross sections on the other sides are looking like that. So that's one way that I think of drawing the pictures, and then I erase the ellipses that I drew, because then I can actually put in nicer looking cross sections like this. So I go like that, and so it looks a little bit like the one that machine drew. better way of observing all the cross sections. See the cross sections parallel to XZ planes are hyperbolas, and the cross sections parallel to YZ planes are also parabolas, and then cross sections parallel to XY plane are the ellipses. Cones. With cones, the equation is x over a to power 2 plus y over b to power 2 equal to z over c to power 2. And again, you get 2 hyperbolas and 1 ellipse. This is very similar to what we had in the previous, the hyperboloid of one sheet. There's only one little difference in there, and so if you plug in, if you intersect with z equal to 0, you realize that the only points that you get are 0, 0, and 0. So intersecting z equal to 0, it gives you that. There are, of course, other pieces that are a little bit different. We are going to compare all of these together in a few slides later. Notice each half the cone is called a nap. So this is one, and this one is the other. One nap, another nap. And also notice that naps are graphs of the functions. Z equal to, solve for z in here, plus minus c square root of x squared over a squared plus y squared over b squared. And so it's each upper half or lower half of the cone also are functions, the graphs of functions. Last, before we start the comparison, is hyperboloids of 2 sheets. So we did the hyperboloids of 1 sheet, and there was a plus in here instead of this negative sign. And now we're doing the hyperboloid of 2 sheets. So how does this one work? Again, when you set, let's say, z equal to a constant, to find the, you set the z equal to constant to find the cross sections that are horizontal, you realize that if k in here is bigger than c, bigger than equal to c, you get values. But if k is less than c, absolute value of k is bigger than c. If absolute value of k is less than absolute value of c, but we're considering c is positive, so not to worry about that, then you don't get any values for x and y. And that's kind of obvious in here. See all these cross sections where k is between negative c and c, there's no value of the surface for those cross sections. But if k is bigger than equal to c, if k is bigger than c, you get all these ellipses. For k equal to c, where basically if you set k equal to c, that's z equal to c, you only get x and y equal to 0 in here. So that is when z is equal to c, then z equal to 0, then z is equal to, so I'm sorry. So when z is equal to c, then you get x over a to power 2 plus y over b to power 2 is equal to c over c to power 2, which is 1, minus 1 is equal to 0. So you get 0 for x, 0 for y, and c. Now if I set z equal to negative c, I also get the same value. So I get these 2 points by setting z equal to plus or minus c. Very much like what we did with the other similar equations. If you set x equal to constant to find those cross sections, or y equal to constant to find those cross sections, you end up seeing a hyperbola or hyperbolas. So 2 ways you get hyperbolas and 1 way you get ellipses. For z between negative c and c, there are no xy solution to the equation, because again then the right hand side is negative and left hand side has to be positive. All solutions have z bigger than equal to c for top sheet, or z less than equal to c for bottom sheet. Each sheet is a graph of the function, so the top part and bottom part each individually are graphs of the function. Now let's compare all of them together. The similar equations together. Hyperboloid of 1 sheet, cone, hyperboloids of 2 sheets, and you notice that one easy way to recognize them, if you don't want to memorize the formula for it, is that if I set z equal to constant for hyperboloid of 1 sheet, and I get, for every constant I get a value, xy value. So and basically there's no tier in between. For this one, if I said z equal to 0, I get only 1 point, and so that's the cone. And then for this one, for a whole lot of values of z, I cannot get anything. That's why there is a tier between the 2 sheets, and it's a hyperboloid of 2 sheets. So the cone you will have, and this could rotate, it could be they could be cones or hyperboloids of 1 sheet or 2 sheets along x-axis, y-axis, or z-axis. But for me to easily recognize them is that I leave and basically I write them always in the same manner that is in here. So I find the 2 with the same sign and I put them in one side, and I put the other one with the other sign to the other side, and the constant with the single term. If there is a constant, cone doesn't have the constant. And then I realized that, for example, hyperboloid of 1 sheet is along z in this case, and cone is along z-axis again, and hyperboloids of 2 sheets are along z-axis. And then I find the difference by cone doesn't have that constant, and between these 2, one will produce values for all z's, the other one doesn't produce values for all z's. That's it. And the only part that is remaining, so ellipsoid is also similar to this, but then when you try to put all the variables of the same side, all 3 end up in one side, and so you know that's an ellipsoid. Okay, between the again, for a comparison, let's look at this. These are all the equations. Z squared equal to x squared plus y squared plus a. When a is positive, you will get the hyperboloid of two sheets. When a was 0, you saw the cone. Then when a is negative, you see the hyperboloids of one sheet. So a negative, hyperboloids of one sheet. A 0, it's coming right there. And then a positive, you get hyperboloids of two sheets. Okay, let's do a few examples. Sketch and identify the graph of z equal to 3x squared plus 4y squared and b z equal to 2x squared minus 5y squared. And so there's a whole lot of difference. I can see that these two are going to give me ellipses, and I can see that this one is going to give me the cross sections. So I get ellipses and I get parabolas, and this one I get hyperbolas and parabolas. So one thing, do they pass the vertical line test? Yes, both of these two do. Intersect with c equal to x equal to c. Those are the horizontal planes. I'm sorry, those are planes that are parallel to YZ. This one gives you parabola up, this one gives you parabola down. X with y equal to c, these are parallel to xz planes, and first one gives you parabola up, the other one gives you parabola up also. With z equal to c, one gives you ellipse, the other one gives you hyperbola, and so you end up with the first one is an elliptic paraboloid, the second one is the hyperbolic paraboloid. And so let's see, when I'm trying to do the elliptic paraboloid using the information given here, parabola up, so I put those parabolas in there, and I know it goes like that, it goes like this, but then I remember also that the cross section, the vertical ones are ellipses. So this sort of gives me an idea of how to draw the graph basically. Again, both of these are graphs of functions because they pass the vertical line test. Sketch and identify the graph of 4x squared minus y squared plus 9z squared plus 4. Again, I like to put the two variables that have the same sign, the two terms that have the same sign, with variables that have the same sign on one side, and the constant, you can vary with the constant, however you can remember, that's fine, but I'm taking the constant to the other side also. So in this case, I can see that if y is less than 2, if y, I'm sorry, the y is between 2, sorry, y is less than 2 and bigger than -2, then I don't see any cross sections for, I don't see any x and y values. And then I realize that there are cross sections that are ellipses, therefore this should be one of those hyperboloids of two sheets. So again, rewrite it the way what we started with was that we took the two variables, keep the two variables on one side, took the other one with the different sign to it. The other side, if you want to have exactly the same in standard form, of this, then you have to divide all by 4, so you can get a 1 over here basically. And then you see that for x equal to constant you get hyperbolas, for y equal to constant if y, the absolute value of y is bigger than 2, you get ellipses. If the absolute value of c is less than 2, you get nothing. For z equal to c, you get hyperbolas. And again, for y equal to 2, you get the 2 points in here. For y equal to 2 and y equal to -2, you get 2 points. And again, here it lies on y axis rather than x and z this time. Hyperboloid of 2 sheets. So let's do a few iClicker questions. iClicker question 12.6a, and which of the following is graphed below? A is equal to x minus 3 to the power 2 plus y minus 1 to the power 2. B equal to x minus 3 equal to y minus 1 to the power 2 plus z to the power 2. C, y minus 1 equal to x minus 3 to the power 2 plus z to the power 2. D, x minus 3 to the power 2 equal to y minus 1 to the power 2 plus z to the power 2. And so how do we go about this? Let's take a break and solve it and come back. So what I see is the basically the I see the paraboloid, and the paraboloid, the vertex of the paraboloid is at 3, 1, and 0. So however it works, the and the options that we have are all basically shifted. See, x minus 3, y minus 1, and z minus 0, and all of them are like that. So that's not an issue at all. And the next part is to notice which direction is the paraboloid opening up. Paraboloid is opening up on the y direction. So among all of these, I have basically C is the one that opens up in the y direction. And if you intersect the this one, C, choice C, by y equal to constant bigger than 1, and you end up with these ellipses. And if on the other intersections will give you parabolas. So C is the answer. So iClicker 13.6 A, and the answer is C. Now let's do iClicker question 13.6b. Identify the graph of 9x squared plus 4y squared plus z squared equal to 1. And take a break and come back and find the answer and come back. So here I see that, I hope you guys found the answer already. I see that all the terms with the variables are on one side and they have the same sign, and this is basically, and the other side is a positive value, therefore this is an ellipsoid. And if you set any of them equal to a constant for certain values, you will get ellipses basically. Now iClicker question 13.6c. Identify the graph of x squared plus y squared minus z squared equal to 1. Maybe stop the recording and come back and find the answer and come back. I hope you tried to find the answer, and so let's see how this works. Basically, here I get x squared plus y squared equal to z squared plus 1. And for all values of z, I will have, and if I cross the surface with z equal to constant, for all values c, I will get ellipses, and or basically this time is circle. So A is the answer. I click here, question 13.6d. Identify the graph of x squared plus y squared minus z squared equal to -1. And stop the recording and solve and come back. I hope you stop the recording, so let's try to solve it together. I put the variable that has different sign to the other side, and what I end up with is I can see the cross sections. If z is bigger than the absolute value of z is bigger than 1, I see all the cross sections are circles, which is a form of ellipse, and I see that there is no intersection when the absolute value of z is less than 1. Therefore, it's hyperboloid of two sheets. I click here, question 13.6e. Identify the graph of z equal to x squared plus y squared. In this case, let's take it, stop the recording and solve and come back. In this case, I see that if basically for not all of the variables are to power 2, and therefore one of them is to power 1, and I will end up with a bunch of parabolas, and for z less than 0, we cannot solve the equation. So this is going to be elliptical paraboloid. Again, for let's say x equal to k, you get upward parabolas. For y equal to k, you get upward parabolas, and then for z equal to k, for k bigger than 0, you get ellipses, and for z equal to 0, you get 1 point, and that's the elliptical paraboloid.